Okay, in our last video we took a look at solutions and we said that a solution is composed of a solute and a solvent. So what I want to do now is really zoom in on that process and imagine what's occurring at the molecular scale. So imagine down here that we throw in sodium chloride. So sodium chloride as a solid is going to be this crystal lattice down here. So this down here would be our solid. However, if we put sodium chloride into water, we know that eventually it will dissolve. And so what's happening? Well, these water molecules that are floating around are actually going to bump into that solid and dislodge some of those cations and anions. So let's just make a little note here. So water or solvent will bump into the solid and help break up the ionic bonds. Okay, so when this happens, we end up with something called hydrated ions. So let's take a look at what a hydrated ion is. And I like this little image right here. But a hydrated ion is an ion surrounded by water molecules. Essentially, they form like a little shell around these ions. And water molecules, if you remember, are acting as our solvent here. And this is going to be true for both cations and anions. The main difference between the two is which side of the water is facing the ion, right? We know that opposite charges attract. So if we think about the net dipole in water molecules, they tend to be pointed towards the oxygen side. So over here, if we zoom in really close, we can see that we've got a negative charge on the oxygen side of the molecule. That means that the hydrogens have these partial positive charges. They're not full positive charges, but they show it here just to give you that idea. And because of that, the negative charge essentially wants to be surrounded by these partial positive charges on the hydrogens in water. Those opposite charges are stabilizing. But let's go in and look at the cation. Well, the cation is going to be a little bit different, right? The cation, because it has a positive charge, is going to be attracted to the oxygen side of the water molecule. So when the shell forms around that cation, all of the oxygen heads in water are going to be pointed in. Versus with anions, we said all of the hydrogens are going to be pointed in. So it is a little bit weird to think about. I know this is hard to take notes on, which is why I think a video works well here. But at the molecular level, these water molecules are going to bump into the solid, dislodge these anions, and then just surround them in a shell of hydrated water molecules. All right, let's take a look at a different situation. So this top one was for ionic compounds. Let's take a look at the bottom one. In fact, let's go ahead and try to separate all of this. Whoops. And just clean up our notes a little bit. So this is for ionic compounds or solutes. But we know that not all solutes are ionic. What if we have a covalent compound or solute? What will that look like? Well, there's another really good image in our book. So let's pull that up. And down here, you can imagine that we've got something solid like sucrose. So this would be our solid covalent compound. Or solute. Okay, same idea. If we have sugar, sugar's covalent, these water molecules over here will start bumping into that solid and essentially dislodging the crystal structure within this covalent compound. But same idea, we're going to have some hydrated molecules, meaning they're going to essentially get wrapped up by water. So let's go ahead and really zoom in on one of these. And I'm just going to pick one of these. So let's go ahead and zoom in over here. Okay, so in sucrose, just standard table sugar, you might have one end that's positive and one end that's negative, meaning it's a polar molecule. Sugar is very polar. So what ends up happening is that the partial positive hydrogen on water will get attracted to the partial negative end on our sucrose. If we've got a partial positive, that's going to be attracted to the partial negative on water. So it's going to orient itself a little differently than with anions, depending on where the partial charges are within the covalent compound. However, this leads me to the next important rule. And this is a good rule of thumb. In fact, that's what we're going to call it. And the rule of thumb is quite simple. It basically states that like dissolves like. You might be wondering, well, what in the heck does that mean? Well, let's break it down into some easy explanations. And what this means is that polar solvents dissolve polar or ionic solutes. Okay, non-polar solvents dissolve non-polar solutes. And it can't be ionic because if it's non-polar, it's definitely ionic. But this is the general trend, right? So the polar solvents dissolve polar solutes. Non-polar solvents dissolve non-polar solutes. A common way I remember this is if you ever get grease on your hands, polar solvents like water won't get grease off your hands, right? Because water is a really poor solvent for grease. However, if you have something like cooking oil in your house, you could grab some cooking oil and get that grease off of your hands by kind of scrubbing your hands with some cooking oil and then washing your hands with soap and water. So different things have different solubilities depending on the solvent that we're using. So that's kind of the general idea. I did want to make a little note here. Okay, and this note is that not all ionic compounds are soluble in polar solvents. In fact, we saw that in our last video, right? We saw that things like calcium carbonate aren't soluble in water despite the fact that they're ionic. So this is, yeah, it's a good rule of thumb, but it's not an across the board absolute rule. So always take this with a grain of salt, no pun intended. You like what I did there? All right, so let's take a look at our next table. So table 7.4 starts looking at solubilities, and this kind of helps determine, well, which ions are soluble in water. And there's a few tricks you can use for this. The simplest one I used when I was in college was nag, sag, because believe it or not, sagging of pants at my high school was a pretty big deal. I went to a Catholic high school, and the priests did not like the boys with saggy pants. All right, so nag sag was how I remembered this. The first one is that nitrates are soluble. Okay, so you can see up here we got nitrates on the list. Next ones are acetates. So acetates tend to be soluble. And then G is a little bit generic, but this is group 1A ions are all soluble. All right, and then S, if we go down, is sulfates. That's down here. That tends to be soluble. A is ammonium. That's the NH4 cation. Those tend to be soluble. And then the last one is G for group 7A. And if you look at that, that's things like chlorides, it could be bromides, iodides, things like that tend to be soluble. So if this helps me remember the solubility rules to a good extent. There's always exceptions though in chemistry, and it drives everybody nuts. But you can see some of the exceptions over here. The main ones to always watch out for are going to be things like mercury salts. Those aren't very soluble. Lead salts tend not to be soluble, and then silver salts of chlorides tend not to be soluble. But to be honest, this is a lot of minutia. I'm going to not expect you to memorize all of the exceptions, but if you can remember this, that would be pretty helpful for just a broad stroke view of solubility rules within chemistry. If you go on and take general chemistry, you may have to remember these in more detail. All right, so let's take this even further and talk about one important note. And this note is that solubility is different than the rate of dissolution. So just because something dissolves slowly doesn't mean that it's not soluble, right? In this case, the rate is impacted by a few things. The first is surface area. So you may notice if you, let's say, get big granular sugar, it doesn't dissolve as readily as something like the ultra fine sugar that you use while baking. And that has to do with the surface area. So if you want things to dissolve faster, all you need to do is grind it up, right? So things that are soluble will dissolve faster if ground up. The other thing that obviously impacts the rate is going to be heat. Most solids, like we saw in our last lecture, will dissolve more readily at high temperatures. That impacts the rate. And then the last one, you probably know this if you ever add sugar to your coffee, is it dissolves faster if you stir. These are all different than solubility. This is rate, meaning how fast things dissolve. Okay, so the last thing I wanted to look at here is going to be solution formation and heat. And this is kind of an interesting one. In fact, there's a lot of good real-world examples. But the first thing is, let's take an endothermic reaction. Okay, what this means is that we're going to have a solute plus solvent, but because it's endothermic, we need to put heat in. And then we'll get our solution out. So what this means is that heat is absorbed. Okay, a good example of this is the cold packs. So if you have an instant cold pack, usually that's a nitrate salt acting as your solute. And when you mix it with solvent, it will absorb heat and thereby feel nice and cool. So these endothermic solutions are great for cold packs. So instant cold pack. I'm not sure how many of you have ever actually used one of these, but they're pretty fun to play around with. It's actually a pack of the solute surrounded by a bag of water, and when you break them, they mix and absorb that heat. All right, the next ones are going to be exothermic. There's essentially solutes when you add to a solvent will create a solution and then kick off heat. So rather than absorbing heat, it means that heat is released. And you might be thinking, well, is this an example of a hot pack? Not exactly. Most hot packs aren't liquid. They're those little solid beads on the inside. But a good example of this would be mixing an acid and water or a base and water. So here's a really quick picture before we finish up, where you can actually do this in a lab setting. In fact, this is a demonstration I normally like to do, but obviously we can't do it in an online environment. But up here, you can see that sodium hydroxide, when you add it to water, will actually take this temperature from about room temperature, which is 23 degrees, all the way up to 38.5 degrees. So this would be exothermic, meaning it releases heat. Versus down here, this is similar to what you might find in a cold pack. So you can see that it starts out at room temperature, and then when you add in the ammonium nitrate, it actually goes down in temperature, which means it's endothermic. All right, I hope that makes sense, but let me know if you have any questions, and I would really encourage you to read this section in the book too, because sometimes it makes more sense just rereading things a second time. Good luck studying.